first question about biomechanics is, which of the following techniques increases strength and stability to an external fixation construct? The answer choices are unicortical pin fixation, decreasing total pin separation distance, increased working distance from the pin to the fracture site, decreasing the distance between the bone and the construct, or using smaller diameter pins. The correct answer is decreasing the distance between the bone and the construct. This image shows what we're generally talking about, a fixation device that holds the bone in place to not let it move and has rods running up and horizontal, so they're perpendicular to each other. The first answer is unicortical pin fixation. In this case, a unicortical pin is shorter than a bicortical pin, meaning that it goes through less layers, so it's weaker and more susceptible to twisting. Therefore, not the correct answer. The next answer is decreasing total pin separation distance. In this case, it's easiest to understand that this would be wrong because if you think about the two pins being close enough together that they only act as one pin, it would be less stable than two pins separated. The next one is increased working distance from the pin to the fracture site. This means that the pins are farther away from the broken part of the bone. The closer they are to the bone, the more stable it will be. The next and correct answer is decreasing the distance between the bone and the construct. The closer the construct is to the bone, the more stable that it is. So in this case, the closer the plate is, or bar, to the arm, the more stable it will be. The final answer choice is using smaller diameter pins. This would not work because larger pins are more resistant to force. Overall, the best way to increase strength and stability to an external fixation construct is to decrease the distance between the bone and the construct. The second question is, in the stress-strain curve, the irreversible change in length after removing the load during the plastic region is called elastic limit, proportional limit, breaking point, ultimate strength, or plastic deformation. The correct answer to this one is plastic deformation. Overall, all of these points can be seen on this stress-strain curve. The first one, elastic limit, is at point P, and this is the point where below it, the material can still recover to its original shape. The next answer choice is for the proportional limit, which is found at point A, and this is the linear region of the graph, in which below it, the stress is directly proportional to the strain the material is feeling. The next one is the breaking point, which is F. It's also known as the point of fracture. The next one is the ultimate strength, U. It's the greatest amount of load the material can handle. The final and correct answer is plastic deformation, which is the area of strain between EY and EF. In this case, all deformation is irreversible. Overall, in the stress-strain curve, the irreversible change length is the plastic deformation, found in the region from EY to EF. And here are some additional study resources.